Hi everybody, so this is a continuation really of factoring and probability as well. We're going to be factoring a very specific type of situation, which is when we have a binomial, which happens to be a difference of two squares, and we'll talk about what that means in just a minute. Let's take a look at this first example. So we have nm squared minus 49. Now this looks a little bit different than the trinomials that we've worked with, but we can kind of approach it the same way if we think about the middle term as having a coefficient of 0. So what I mean by that is that if you have 9m squared plus 0m minus 49, you could certainly rewrite this little binomial this way to show it kind of in its trinomial form. And if we were going to factor that, we can use the same little diagram we've been using this whole time. And what's interesting about this one is that we know that each of these, of our two kind of side terms here, have to add to be 0. And we know that opposites add to equal 0, so this can be really helpful when we think about this. The 9m squared, well, we're going to deal with the 3m's. We could have a 9m and an m, but in this case, actually, we're just going to have that first term be the same, the 3m. And we just say, okay, well, now I need two things that multiply together to equal 49, and really two things that add together to equal 0. The fact that this is a square, which is minus 49, it's a perfect square, means that we could square root the positive 49 and get 7. So a positive 7 and a negative 7 are going to multiply together to equal negative 49. And what's great about this is that the negative 7 and the positive 7m are going to cancel each other out when we multiply these together, which means ultimately that we would end up getting 3m minus 7 times 3m plus 7 as our two binomials. Now, what's really nice about this is that if we kind of recognize something really early on, which is that we have a 9m squared minus 4y, we call this a difference of squares because you can square root each of these and get a positive integer, right? So if you square root 9m squared, you get the 3m, and if you square root 49, you get 7. So this kind of pattern exists for factoring differences of squares, is that we would say, okay, 3m minus 7, 3m plus 7. So if we go down here to this next example, we have negative 4 plus x squared. Well, if I reorder that to put the x squared in front, because that's kind of the typical way that we look at this, I could rewrite that as x squared minus 4. Now, once again, I'm going to recognize this as a difference of squares, meaning that I can square root the x squared and I can square root the 4. So I can write this as x plus 2, x minus 2. Again, I'm kind of skipping that kind of factor diagram here that I did for the first one because I'm recognizing the pattern, right? I know that if I multiply 2 times negative 2, I'm going to get negative 4, and I know that my middle terms are going to cancel each other out because my middle terms would be 2x and negative 2x, right? So my final answer is x plus 2 times the quantity x minus 2. All right, down here, I want a difference of squares. Right now I have this addition thing going on. I'm just going to switch the order of these terms. And what I have, once again, are two things that I can, that are perfect squares, which is 25y squared and 36a squared. The middle term is gone, so I'm just going to follow the same pattern. Well, if I square root 25y squared, I'm going to get 5y. So I know that that's going to be my first term, right? Add 6a minus 6a. That'll assure that my middle term will cancel. And there we have it, using that differences of squares pattern. All right, let's go down to this last example for this one before we move on to probability. So this time, Once again, we've got this kind of order switched. I want to have some subtraction going on, and then if it's a difference of squares, that means it has to be subtracted values. So I'm going to just switch the order, so that'll allow me to subtract one from the other. And once again, I recognize that what I have going on here is a difference of squares. I can square each of these, or write them as two things being multiplied, two of the same things being multiplied together. So if I start out with the 49a squared, I can say, okay, well, if I square rooted that, I'd end up with 7a. So that's going to be my first term, to be multiplied together, right? And my second term, okay, 36x to the 6y to the 4th. Well, if I square rooted that, I would get 6x to the 3rd, y to the 2nd. So I'm going to add 6x to the 3rd, y to the 2nd, and I'm going to subtract 6x to the 3rd, y to the 2nd. And in doing that, once again, my middle terms will cancel if I FOIL this, and we'll be all set there, which is exactly what I want. Let's take a look at probability, this time focusing on a contrast between replacement and no replacement, or with replacement and without. Container has 4 red marbles and 7 blue marbles. 2 marbles are drawn at random. What is the probability that the first is red and the second is blue if the marbles are drawn with replacement or without replacement? So if we look at A, with replacement means that we're just, after we draw the first marble, we put it back in before we redraw the second marble. Versus without replacement, which is that we pick a marble, we set it aside, and then we pick another marble. So it actually does change the probability in the second draw, unlike with replacement, and let's see how that works. So let's talk about probability of red than blue. So first of all, the probability of pulling a red marble is actually 4 out of a possible 11 choices, right? And if I put that back and then calculate the probability of pulling a blue marble, well, that would still be 7 out of 11 choices. If I multiply those two probabilities together, I get 28 out of 121 as my chance of pulling a red than a blue with replacement. So this would be my final answer there. If we go to a without replacement situation, things change a little bit. If we look at the top, the probability of pulling a red is still 4 out of 11. What changes here is that when we go to pull the blue, well, this time we've discarded one of the marbles, so we've actually discarded one of the possible outcomes. So that means that we actually have a 7 out of 10 chance this time of pulling a blue marble on the second draw, assuming we picked a red on the first. We can simplify that a little bit before we multiply across, recognizing that 4 and 10 have a factor of 2, so we can divide those out beforehand. And that leaves us with 14/55 as our chances without replacement of that situation happening. Give these a shot. Hi everybody, so this is a focus on scientific notation. Scientific notation is a very specific way of writing values. It's used in the scientific fields to write numbers that are really big or really small. And one of the ways that I like to think about this is to kind of think of this kind of format. So I'm going to kind of write this on the side here. If really the way that scientific notation is written is that it's one digit in the ones place, point whatever the rest of the digits are, right? And then you multiply that times 10 to some power. Now if it's to the 0 power, we know that anything to the 0 power is 1. I'm just going to put a focus on this exponent for a minute. And this tells us where the decimal point really belongs in this number, real position. So again, hopefully with some examples, this will become a little bit clearer. Essentially, you're going to be moving the decimal point to the right that many places if the number is greater than 1, and to the left, if the number is less than 1. So essentially, we're kind of dealing with a situation where if the number is greater than 1, then it's going to be a bigger number, and if it's less than 1, it's going to be a smaller number than what you see there. So I'm going to kind of demonstrate this with a few examples where I'm going to be writing values using scientific notation. Let's look at this first example. So right now, this is, let's see, I need to even figure this out. So we have thousands, 10,000s, 100,000s, millions. So this is 316 millionths. And we are meant to write this number in scientific notation. So the first thing that I notice from my little, what I just wrote here on the side, is that I need a digit in the ones place, dot the rest. Well, that means that the first number in this scientific notation is going to be 3.16, right? Because 3 is my first non-zero digit there. I'm going to multiply that times 10 to the power of something. And now I need to figure out what my variable is going to be. So since this value is less than 1, it means what I always do is that I kind of put the value in there, and I say, okay, this is where I put the decimal point, and I had to move it 1, 2, 3, 4 places to the left in order to make this that value. So because it's moving to the left, I would put -4. So 3 16/100ths times 10 to the -4 is the same as 316 millionths in standard notation, or kind of numbers as we know them. Now we're going to kind of go in the opposite direction here. Now we have 316 millionths times 10 to the -7, and we're meant to write that in scientific notation again. Actually, we're not going in the opposite direction, we're just fixing this. What's wrong with this right now, and the reason that this is not currently in scientific notation, is that it doesn't have a non-zero in the ones place, right? It's got a 0 in the ones place. So if I adjusted or wrote this part, kind of using scientific notation, I would put 3.16 times 10 to the, again, 1, 2, 3, 4, 10 to the -4th, times 10 to the -7th. And this is not in scientific notation because we've got 2 powers of 10 here. But I can multiply those together, and I can get 3.16 times 10 to the -11th by, again, kind of using that product of powers rule of exponents. So here we are. Now this actually falls into what proper scientific notation should look like. I should circle my answer up here too. All right, let's look at this third example. So now we have 39,423,000, and we're meant to write it in scientific notation. All right, first thing I do is that I need one digit in the ones place and the rest of them in decimal places. So I look at this and I say, okay, it's got to be 3.9423. I don't need to include the zeros because there's nothing after them. And I need to multiply that times 10 to the power of something. Well, this time we're dealing with a larger number, which means that we really need to send that decimal point to the right, which means multiplying by a power of 10 that has a positive integer in it. And how many places did we have to move it? Well, I always put my digit here, and I say, okay, 1, 2, 3, 4, 5, 6, 7. So that means it would be 10 to the 7th. And by the way, if you plug this into a calculator, 3.9423 times 10 to the 7th, you should end up with 39,423,000. So you can check that as well, kind of as you go through these. All right. Down here, similar type of situation where we've got this thing that almost looks like scientific notation. The problem is that the decimal point is not in the right place in this first value here. So what I'm going to do is I'm going to write it as a power of 10, which would be 3.16 times 10 to the, okay, well, if I was going to do that, it would be 1, 2, 3, 4 places to the left, which means a -4, times 10 to the 7th. And again, we're getting closer here, but we still have to kind of reconcile our powers of 10. 10 to the negative fourth times 10 to the seventh is actually 10 to the third power. And so now we've got 3.16 times 10 to the third power as being our final answer. Again, you can take this value up here, you can plug it into your calculator, and you can take the value that we just created, plug it into your calculator, and you should get the same value when you do that. So you can kind of check these as you're doing your work. Give a few of these a try and see how you do.